Thank you. Okay, so the idea driving my work, my research, is in a brief summary, is the crystalline flame. And really, that's a metaphor for the reciprocal relationship between form and process. The form is the crystal, and the process that generates the form. And they have this reciprocal relationship. They cannot exist without each other. You find that also in terms of discrete and continuous phenomena. In the 20th century, we found this in the particle and wave phenomena regarding matter, where things are particles, depending on the instruments that are reading, and then from other instruments read wave phenomena. So really, you're looking at the same thing. So the crystalline flame is this metaphor for this reciprocal relationship, this ambiguity. And pattern integrities is actually quoted, it's a quote from Buckminster Fuller, who really looked at a lot of these structures that are crystal and flame in nature. And the best way to sort of describe this is really vibrations in fluids. Vibrations in fluids depending on the kind of frame or the kind of pan that would contain a fluid, and the vibrations that are being, the fluid is being subjected to, or you might think of interacting frequencies, you start to get a resultant pattern in the liquid, in the fluid. And that pattern, if the frequencies are constant, that pattern is constant. It looks static. But through that pattern, there are these wave patterns flowing through that. And the examples on the right are, again, the kinds of patterns that you get from these fluid interacting vibrations. On the lower right, you have two frequencies, one from the right and one from the left. The two are interacting, and you get this pattern. You also get it on the upper right. It's platinum, the microstructure of metals. You find these vibrating patterns that are constant if the vibration is constant, yet at the same time, through it, you have this incredible dynamic activity that's contained within that pattern. And more recently, through computer analysis and visualization, we started to analyze more complex phenomena, like, for example, the weather, and we're starting to get these what are called attractors, chaotic attractors. On the lower left, you have a Lorentz attractor where they modeled the weather. And once again, you find a contained space within which there is dynamic activity. What is different there, though, is that the activity, it's actually modeled, so time is compressed. So an incredible amount of time is compressed, yet at the same time we find the similar structures. So you can do the ones with water, you can do that at home. The other ones, you need a more complex analyzing instrument like the computer. Now, a major influence in this work is the work of Leonardo da Vinci and his analysis of turbulence, his insights into vortices, coiling structures, and spiral motion. He was very, very much in love with trying to understand nature. He's a quintessential Renaissance scientist, artist. And on the right, you have one of his very famous deluge drawings, where he's trying to really capture this dynamic activity. He's on a hill, he's looking at a dynamic turbulence, and he's trying to draw and capture this. Also, he made a lot of analogies between, or compared a lot of phenomena where you find very similar structures. And on the middle, you have his analysis of bird flight and how birds use wind and air currents. And he was way ahead of his time. And when you compare these drawings with a more modern analysis and understanding by the work of Stephen Vogel. And even more interesting in terms of computer analysis is this fractals, where you have self-similarity at different scales of visualization, where you have a certain structure. As the more you zoom in, that same structure keeps coming up over and over again. So you have that self-similarity. And what is interesting to me is how a hologram is also very much like fractal. A hologram is really a plate that has a recorded interference pattern, and that interference pattern is a certain amount of time within which you can see motion as you move your head. And if you fracture that plate, every fragment contains the whole image that the larger plate contained. It's not as focused, but the same amount of information is there. So a hologram is in a way is also fractal in terms of its structure. Also, the work of Buckminster Fuller was very insightful in terms of the crystalline flame, and he asked us to compare the similarities between all these kinds of structures, the structure of tornadoes that can get as complex as 3 vortices interacting, the structure of rope, the structure of knots, as well as the core of a fruit, which actually has a very subtle electromagnetic field, the Earth's magnetic field, a magnet, and a torus. So in a way, a torus is a very basic shape in dynamics. And then also a nuclear explosion. So he says there's something about this that keeps coming up at different scales of analysis. So one of the things I did, which was very, very fruitful, I did many things trying to work through this process. I literally had a potter's wheel that I mounted to a ceiling in my studio, and I started just hanging a string or a loop and spinning it. As you see on this image here, this is really the way it is, but I like to show them upside down because I'm interested in these structures that look like columns, for example. So from the left to the right, the speed is increasing, and you get these structures that can remain static if the speed remains the same. As you speed it up, there's a certain point where another structure shows up. So this is a string. This is another single string. This is a loop. These are loops that are the speed is increasing towards the right. And then this is also increasing towards the right. So I literally say I put a Ariadne's thread, a reference to Greek mythology. I won't get into that at the moment, but Ariadne's thread is guiding us through this chaotic vortex, chaotic labyrinth. I also recorded this process by literally the camera being on the floor, recording the string as it's spinning, as you see here, as well as mounting a camera to the potter's wheel. So it was spinning with the string, and these are stills from that video. And this is another still from that video as well. This one is looking up into the string as it's spinning. And then on the top here, I improvised. I took a lot of these stills and I just collaged them together tangentially, just to see the kinds of patterns that would emerge from this process. And this reminds me of Islamic calligraphy, the painter Miro, his line, the fluidity of his line. And then also recording the string just arbitrarily from different angles and different exposures, and just trying to see the kinds of forms that were being shaped by the spinning string. Very, very complex, and also trying to look into the core of those forms that were being generated. This is another one where the actual string itself is casting a shadow on the form that it itself is generating. And then also taking a lot of these sweeps and collaging them tangentially to try to see the kinds of shapes, the inner shapes that can be created through this process. And is it possible to build these kinds of spaces? And how would one go about this? So a major influence in that goal is a book on growth and form by D.R.C. Thompson, where he asks us to visualize these deformable matrices that are invisible, that you can imagine them as guiding the developmental process. The developmental process, so for example, this grid, it's deformed, it could generate another type of fish, as well as Louis Sullivan, the architect, and his idea of basic geometric shapes as being dynamic and generative in their potential. So I investigated folding patterns, folded paper with a pattern, folding them. This is the same pattern, just different arrangements, as well as taking bamboo sticks. For example, a square relationship, it's dynamic. Weaving these cells, so a square of bamboo sticks joined with rubber bands, that's a cell, you weave them together into a fabric, like for example here, this fabric is very malleable. You start to explore the properties of that malleability, and and as you get very, very familiar with the process, you're able to make these structures, these sculptural shapes. This is the same structure rearranged. This led to an installation. As I got more and more familiar with the process, it got more and more complex. This is different views. This structure here, you look at the mirror, and this is the pattern that you actually see. So you see very, very spiral shapes going through the structure. Sometimes it looks chaotic, and from another angle, it looks very structured. Another installation inspired by Leonardo da Vinci's deluge drawings, where I improvised an arrangement on the walls, and the shadows were very much like the deluge drawings of da Vinci. And this is work by students, where I give them, each student or a group of students, a cell to explore. And these are the shapes of the structures that they generated. I won't get into the specifics of each at the moment. An installation of their work. The shadows, this one particular structure started to look very, very organic. Again, that was very interesting. And then again, back to folding paper, equilateral triangle of pattern generated a field that was very, very malleable and very generative in terms of what it could form. So I started looking at the possibility of pavilions with this structure. It was analyzed digitally as well. And then also, we did a large installation where we studied the membrane at an actual full scale. This was the resulting gallery installation and the digital analysis on the left. And now we're looking at applying it to imagine this could be a traveling circus or a traveling show. So we're looking at actually applying this membrane. It's all with an equilateral triangle. And this one here is actually a pavilion proposed for the Ottawa Tulip Festival. Every season it could be reconfigured in a different arrangement. Same structure. The next slide is actually a lot clearer. This is another application of the structure. This is in Major Hills Park here in Ottawa. And these animations show the malleability of this membrane. It's very, very fluid characteristics. So this is a way of being able to really study the membrane larger, because we can only make so much of it with our hands. Through computer analysis, we're able to analyze this and start to look at actual larger structures, larger applications of the membrane. Again, the fluidity, it's something that this is modeling a behavior that we studied through our hands. The very, very important point, because you cannot find these kinds of properties through computer analysis. You need to actually physically do it, physically experience it, to get to really understand the actual behavior that's generated. And then finally, this is a quote from Richard Feynman, great physicist, also a great bongo player. And he says, nature uses only the longest threads to weave her patterns, so each small piece of her fabric reveals the organization of the entire tapestry. Thank you.